Hello everyone. So in this part, we will look into few more page replacement algorithms. So few announcements. Lab 4 starts this week. So the web page for Lab 4 will be out by midnight. And reading for this part is chapter 19 from the dinosaur book. So we looked at page replacement algorithms. Just to revise, page replacement algorithms deal with identifying a physical page that needs to be replaced so that a new page that is needed by a process can be brought in. So, and the page replacement problem only occurs when under memory pressure. That means when the system is running under full memory capacity, where any page that is needed by a process requires a page from memory to be swapped out. Okay. And here the problem becomes which page in the physical memory to be selected so that it can be evicted out, which is the victim page. And the performance goal for any page replacement algorithm is to minimize the number of page faults for a given set of page references. And here, the intuition behind page replacement algorithms is to find a page that is least useful so that when it is swapped out, the page faults will be less. Or in a hope that the page that we just swapped out will not be used by any process. So here the challenge becomes how to determine the page to be least useful, right? Even if we know about the future, few times it gets tricky. Even identifying a least useful page when we know the future is not as straightforward as we look more on this in this part. So in the last class, we actually looked into a couple of page replacement algorithms. We ended with FIFO, first in, first out with second chance. So here, the algorithm is first in, first out. However, we make a small modification to the algorithm. Here, what happens is we take the oldest page, and instead of blindly replacing the oldest page, we check the reference bit of that oldest page. As a reminder, reference bit is a bit in the page table entry that will be set by the MMU when that page is accessed by any process. Okay. So if the reference bit is set, then we just move the page to the head of the queue. Okay. We make the reference bit 0 and we put the page to the head of the queue. If the reference bit is 0, we replace it. So here, as you can imagine, we give a page second chance for it to be useful. Okay. So pros for this approach is it's fast. In addition to being fast, it also respects the frequency of the pages. That means if a heavily used page or a rather frequently used page will not be replaced because as we use the reference bit, if the page is frequently used, the reference bit will be constantly set. So we don't replace a frequently used page. Okay. And disadvantages of this approach is the worst case time. Here, imagine if all the pages in the queue are actually frequently used, then worst case, we have to go through the entire queue in order to find the page. In worst case, let's say all the pages are heavily used or rather frequently used, then we end up just iterating through all the pages only to replace the first page. Okay. So a modification of these FIFO algorithms is to use a clock algorithm. Here, basically the setting is in case of FIFO, what we do is we move the elements around the queue, right? So instead of that, the clock algorithm goes on observation that instead of moving the elements, why don't we move the index? Okay. So here the thing is we have list of page frames that are possible candidates for replacement. Okay. Basically, this could be all the page frames that we have or that the operating system has. or rather like all the page frames that we have in the physical memory. Okay. And operating system maintains a handle or a clock hand, which let's say it starts by pointing to the first page. So on page fault, we check the page that is pointed by the clock, by the by the hand of the clock, and we see if the reference bit is set. If the reference bit is set, we unset it and we move the clock hand to the next page. Okay. Let's say if the reference bit is not set, then we make that page, we select that page as a victim page, we swap the page out, and we get the page in, and that's our victim page. Okay. And at the end we also we reset the reference bit to 0. We don't need to reset the reference bit because reference bit is already 0. So here, note that we are not moving the elements, rather we are moving the clock hand, which is more efficient than maintaining a queue of physical frames, right? So here we just need to maintain only one index. At any time when we need a page, we just look at the page pointed by the clock hand. We see if the reference bit is 0, then that's our page, that's our victim page. If the reference bit is 1, we just move the clock hand to the next page, and we repeat the process until we find a page where the reference bit is 0. Okay. So here, as you can see, the mechanism, or rather the technique, is similar to FIFO with second chance, but the mechanism is different, where instead of moving the elements around, we move the index around, where the index is the clock hand. So there are a few interesting questions in clock-based FIFO algorithm. So here, what happens when if all the reference bits are 1? So here in this case, note that as we move the clock handle, we actually reset the bit to 0, right? So if the reference bit is 1, we actually set the bit to 0 and we move to the next page, right? if all the if all the reference bits are 1, we go back and we eventually take the first page, because we would have resetted the reference bit to the first page. So the worst case efficiency of clock based FIFO is similar to that of FIFO. However, in this case, we don't need to maintain the queue. Rather, we just update the index, or the clock hand. And there are few interesting uh, scenarios or phenomenons that we can infer based on how fast the clock hand is moving. Okay. So what does it suggest if we observe that the clock hand is moving very fast? Okay, what does this suggest? This suggests that there is huge memory pressure, right? Basically, this suggests that most of the physical pages are actually heavily used, because if the page is heavily used, that is, if the reference bit is 1, that is when we move the clock hand. So fast moving clock hand indicates high memory pressure, and slow moving clock hand indicates the memory pressure is low. Okay. So in the next part, we will look into more interesting page replacement algorithms.